let me just set up my comments, then we can begin. Hello, hello, hope I'm audible too. Set up my comments. Yeah. So hi guys, today we are going to basically discuss the problems for the contest 1076 division 3. Hope you guys enjoyed the problems. And today's contest was very beautiful contest. And yeah, you guys can comment out how many questions did you solve today. Okay, great. So yeah, so like the usual drill, first we are going to discuss the problem, and then we are going to basically discuss what were the intuitions and the observations we could have in the problem, and then we are going to finally jump towards the solution after we prove using the solutions and the intuitions. So yeah, great, let's start. Okay, so yeah, so let me type something. The contest is 1076. Great. Okay, let's start. Great, like I can see some comments. Someone has solved 6 problems, someone has solved 2 problems, and someone has also solved 2 problems. Great, let's discuss the problems. Okay, so let's start with the first problem, the DMBM and the array. Okay, so DMBM had a birthday yesterday. He was gifted an array of n elements and a number x, but there is one problem. He only likes arrays where the sum of elements equals s. Okay, to make the array appealing to him, you can perform the following operation any number of times. Okay, choose an index I and add x to the number ai. Okay, so what the problem has given to us, first let's state that and understand the problem. So this is our first problem, the problem number A, and it has given that we have given an array A, right? So the array would be like this. It starts from A1, it has n elements. Okay, great. After that we are given that to basically make this appealing to him, we want that the sum of elements, which is like the sum of this array A, is equal to s. This is to make it appealing, and we can perform some operations basically any number of times. And what's the operation here? The operation is operation. So yeah, so we can perform some operations here. The operation is we can add x to any element ai in the array, right? So there's 3 things we are given, that there is this guy whose name is little weird, DMBM, and he wants to make an array appealing, and to make this appealing we can basically do some operations. And what the operation is, we can add x to any element here. Okay, great. For example, if he has given the array 1 2 3 4 5 and x equal to 2, we can choose the index 3 and get array 1 2 5 5. Okay, yeah, it's completely fine, right? These are like the basics. Okay, let's analyze this, what he just said. Okay, so he says that we are given this array, right? So how we can perform the operation, and let's say x is equal to 2. So how we can perform the operation, we can add this 2 to any of these elements. Let's say we added to index 3, index 2 actually, let's try for 2. Okay, so yeah, let's say we added it to index 2. Index 2 is this one. So the new array would be 1 2 plus 2, it's 4, 3 and 5. Okay, so this is what an operation would look like. So this is our entire question basically, and we are told what we have to find. The task is to determine whether the array can appeal DMBM after any number of operations. Okay, great. So basically we can do any number of operations like this, right? These operations we can do any number of times, and we have to find out whether or not we can make this array appealing. What's an appealing? This. Whether or not we can make the sum of this array equal to S. If we can make it here S, what we have to do, we have to print yes, otherwise we have to print no. Okay, so if we can make it, if this is equal to S, we have to print yes. If this is not equal to S, we have to print no. Got it? So this was the entire question. This is the entire question. So yeah, great. So now let's also see the input and output constraints. So input, we are given like a classic number of t, number of which stand for number of test cases. Then we are given n, s and x. N is the number of elements, x is the number we can add in each operation, and s is the sum which the sum of elements in the array should be equal to make that array appealing. And then we are given n integers, a1, a2, a3 ... an, right? And each element in the array is less than equal to 10 and greater than equal to 1, right? So it's like pretty standard div3a. It's pretty easy one too. So how are we going to solve the problem? So the question says that perform some operations and make the sum of array A equal to S. Okay, great. So first we have to see something. We have to perform some operations, right? We have to perform some operations. Each operation we can only add the element x, right? And it doesn't matter whatever, this is our observation 1. It doesn't matter whatever element we add. We can add it to a1 or we can add it to a2 or any element, right? Eventually we are going to increase the sum. Let's say the current sum is x by x, right? We can add it to the first element. This would make us a1 plus x comma a2, right? Either we could add it to the second element. That would make it a1 a2 plus x, right? Either way the sum would be same, right? The sum would be the sum of all elements. The sum of all elements is a1 plus x plus a2. In the same way here too, it's a1 plus a2 plus x, right? So either way the sum of elements would be same, right? So it doesn't matter. This is our first observation. What? That we can add x to any number, any element. Okay, great. And that would increase our s by, s is the sum, current sum. That would increase the current sum by x. Okay, this is our first observation. What's the second observation? Second observation is we cannot reduce, right? We cannot subtract. We cannot subtract from s, right? Why? Because x here, the number we need to add is always greater than 1, right? So it's always positive. This x is always positive, right? And we just discovered that we can just add s to the sum. After each operation we would be adding x to the sum, so the sum would just increase. We can never decrease the sum, right? Okay, someone typed he solved 3 questions. Great, dude, great. The fourth one was this one, right? You could have tried the fourth one too. Right, the fourth one was like pretty like average question. Like if you did 3, you could have gone for the fourth one too. The fifth one was like little bit tricky compared to these two, but yeah. Yeah, anyways, like back to topic. We can't subtract s. This is our second observation. Okay, great. And what's the third observation? The third observation is here that the third is basically like based on these two observations. These two are the major observations, right? We can, the first observation, we can only add x to the total sum. Okay, great. The third thing is extension for 1 is that we can also add 2x, we can also add 3x, we can also add 4x to the sum, dot 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 dot. So we can basically add any multiple of x, right? Why? We can, basically if we did operation one time, if the operation what does one time, we would be adding x to any element that would basically add x to the sum that we just observed. What if we did observation 2 twice? It would add twice the x to the total sum, right? And similarly we go there. So basically we can just add the multiples of x to the sum. This is our third observation. And using these 3 observations, basically using these 3 observations, we came to the conclusion. What conclusion? We basically divide the number into some cases. First, if this sum, right, this is our current sum, this s dash, if sum current is greater than s, this is the sum that we need, right, then we would never be able to find the answer. Why? We just discovered we, after each operation that we could do, we cannot subtract from s, right? We cannot reduce from x, right? Yeah. So that's why we would never be able to do it. Okay. So this is our. Now we are just using these observations to form our solution. So this is the first step for our solution. The second one is, let's say the difference. If this is not true, then this s would be greater than equal to our current sum, right? Right. Let's say the difference between them is equal to s, the sum we need, minus current sum, right? And this difference, right, if this difference that we got, right, if this, when we modulo it by x, and this is equal to 0, that means if it's equal to 0, then it would be yes, otherwise no. Okay, let's digest it. So the difference is the sum we need, right? The number we need, the sum we need, total addition that the total sum needs to be such that we could basically make equal the current sum equal to the sum we need, right? So this is the difference. So basically the difference between them, if we modulate by x, like it tells us that using some operations can we basically make the current sum equal to s, right? The current sum we need to make it to s, right? So this tells us that, like, if it's completely divisible by x, that means that there exists some numbers that the number that the times we could do operation would result in small s, which is our total sum. So this was the entire intuition behind it. Okay, hope you guys like this solution. This was like pretty basic one. Here's the entire solution. Yeah, this. Okay, let's also go through us to the, let's just go through the solution to our code actually. Yeah. Actually don't like just ignore the template, it's just for the reference. So yeah, here we are taking input, here's our sum variable, here we are calculating entire sum, and then here's our difference. The first check we do is if difference is greater than less than 0. What does this mean? That the sum that we currently have is greater, right? If this is less than 0, the answer would be no, right? Yeah, absolutely. Otherwise, if this difference, if it's greater than 0, and if it's modulo x, that means that we have some perfect number of solutions. After that, the difference would we could be able to cover the difference, right? So if the modulo x is not equal to 0, we just print no and we move on. Similarly, if either of those conditions does not satisfy, we can move on and basically print yes. Okay, so any doubts from anyone? You can just ping out in comments. And even if you think like if your approach was better or you did something else, you could just inform, not for this question, for any questions, right? So it would be very productive. So yeah, this was the entire first solution. So what we did was basically we made three observations. The first observation was that we could only add x, right? The first observation that we could basically do observation on any element, it would finally be adding the total sum to it would finally increase the total sum by x. Got it? This was the first observation. The second observation is that we cannot subtract from the total sum that we currently have or the current sum, right? We can only add it. And the third was we could basically add in multiples of x. Why? Because after each operation we could just increase the total sum by x. So we could do, like, let's say we did k operations, it would increase the total sum by k times, sorry, total sum by k into x. Got it? Let's say we did k operations. Got it? Using these three observations, we came to the conclusion that if the current sum is greater than s, as we cannot decrease, observation number 2, it would be complete no. And then we calculated a difference, and we thought that as we can only increase in multiples of x, if this difference is not a multiple of x, that means that its modulo x is equal to 0. That modulo x is not equal to 0, then the answer will be no. Otherwise, if it's a multiple of x, great, the answer would be yes, because we would be able to cover, right? Let's also understand an example. Let's say we had 1, 2 and x was equal to 9, x is equal to 3 and s was equal to 9, right? The current sum would be, this would be equal to 3, right? Is the current sum less than s? Yeah, right. So we would basically move to this block, and then we will check if the difference, right? We basically check the difference. The difference was the sum we need 9 minus 3, which is equal to 6. And then we check if this is divisible by x, which is 3. Yes, it is divisible by 3. So the answer would be yes. And how many operations we need? 6 divided by 3 equal to 2. Right? These many operations we need. Let's try actually. Let's do one operation on this index, one operation on this index. So the final array would be 3 plus 1, 4, 2 plus 3, 5. Right? The sum is here 9. So great, we solved the solution. Now let's move towards the second solution. Okay. Reverse a permutation. Great. A permutation of length n consists of n distinct integers from 1 to n in arbitrary order. Okay. For example, 2, 3, 1, 5, 4 is a permutation, but 1, 2, 2 and 1, 3, 4 are not permutations. Okay. You are given a permutation P of lengthen. You can perform the following operation exactly once. Okay. Choose two integers L and R such that L is greater than equal to 1 and R is less than equal to n, and reverse the segment LR in the permutation. Okay. Your task is to basically output the lexicographically maximum permutation that can be obtained by performing this operation. An operation is A lexicographically greater than operation B, first position at I where the differ holds AI greater than BI. Okay, so great question again. Let's discuss the solution too. So yeah, so this is question number B, right? Let's actually use a bolder one. Okay. Yeah. So in this B question, let's first extract the problem statement. So the first thing first that we came to know that what's a permutation? Permutation. A permutation is basically arrangement of all numbers from 1 to let's say n such that each appears single time, right? Single occurrence for each element. Single occurrence, right? So that's a permutation. First they told us about the definition of permutation. Okay, great. But we were already aware of it, right? Because we are smart. And again, the second point that they told us was that basically, let's go to the problem statement. We are given a permutation P of lengthen. Okay, great. And we can perform one operation. We can perform exactly one operation. And what's the operation? We are given this permutation P. Okay, so this would be something like this dot 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 and like some arrangement of these numbers. Because of this is length n, it would include each number from 1 to n exactly once. And then we have some operation here again, like the classic code forces. So yeah, what operation we have? We can choose L and R, right, such that these L and R are greater than equal to 1 and less than equal to n, and we can reverse that portion, reverse that subarray. Reverse the subarray. Okay, so how are we going to do it? And then the final operation, what we need to find? Okay, this were given, and what we need to find? The lexicographically maximum. Lexicographically maximum permutation of the permutation or lexicographically possible array that we could find. Okay, so this is the entire question. Let's actually break down. First we will understand about the operation first, and then we'll understand what's lexicographically maximum array means, and then we are going to move towards the observation. So first let's understand reversing an array. Let's say we have, what does this operation means, and we can only perform this operation once, right? And what we can do is basically, let's say we have this number 1 2 3 4 5. Is this a permutation? Let's assume this is a permutation, right? What we can do is we can make any subarray. Let's say we took this subarray and we can reverse it. What they have told us, take two integers L and R and reverse this segment in the permutation. So basically, let's say we took L equal to 2 and R equal to 4. We can reverse this permutation, we reverse this portion, this segment, and it would be L 4 3 2 and 5. Got it? So this marks our single operation, and we can only do single operation, right? Let's one more thing, like let's actually see one more thing. Can we perform no operations? But they have told us to perform exactly once, right? So exactly we have to perform at least once. But what if I choose this array? Like let's assume again we have this p dash array which is equal to 1, 2, 3, 4 and 5, and we choose l equal to 3 and r equal to 3. We can choose it, right? The constraints here, l is less than equal to r, yeah, and we basically reverse this segment, so this would result in the same array, right? So don't worry, like yeah, we can perform no operations theoretically basically. Okay, got it. So this is an operation. Okay, and now what's lexicographically maximum array? Lexicographically maximum tells us that, you can also read the definition here to about the lexicographically maximum array. A permutation A or the array A is lexicographically greater than permutation B if the first position I where the different holes AI is greater than BI. That means that let's say we have two arrays 3 1 2 4 and 3 1 4 2, right? We start from the leftmost side, we start from 3. Are they both same? Yeah, they are same. Are they both same? Yeah, they are same. Are they both same? No, they are not. And then we check which has the greater number. This has the greater number, right? Let's say this array is A, this array is A, this array is B. This here the both arrays are different, right? But here, as this the element B has a greater number, the lexicographically larger array would be the array B, right? To compare which array is lexicographically larger, we start from the left and we just start comparing each element, each index, elements at each index for both the array, and then we find out wherever the index at which both arrays are different, we basically check which one has the larger element. So this is lexicographically maximum array. Got it. So this is our entire question. Now let's move towards the observations and all. First let's understand the question. Okay, how can we make some array? Let's say we have some array A, have some permutation A 4 3 1 2, right? How can we make this maximum? To make this maximum, as we have realized, we start from left, right? So we need the largest element from the left, right? So yeah, is 4 the largest element available? Yeah, it is. Let's put it here. Then is 3 the largest element available apart from these? Yeah, this. Is 1 the largest element here? No, it's 2. So let's mark 2. And the remaining element is 1, so we mark it 1. To make this lexicographically maximum, this is observation 1, we need elements in descending order, right? We need the maximum element leftmost side. Right, so this tells us that to basically make any array lexicographically maximum, or to basically check, right, or basically convert which would be the maximum lexicographically maximum permutation, we basically, the permutation which is in descending order would be the lexicographically maximum, because we start from the left and all the greatest number possible is at the best number possible is at its index where it should be, right? So this is like the first observation, right? Like if you are already aware of lexicographical order, so this was pretty easier to find. Just once actually move forward, right? Okay, yeah. So this was our first observation. What's the second observation? So we know something, right? That we are going to start from the leftmost array to the rightmost index, right? We are going to start from the leftmost part or leftmost index, which is the index 1, to the rightmost index, which is index n, if we take one based indexing, right? So what we could do, let's say we have this permutation, what we could do using our operation to make it maximum, right? The maximum array that it should be like 4 3 2 1, right? Lexicographically maximum array, right? But we cannot make it 4 3 2 1, right? Because we only have one operation, and the operation says that we have to choose some segment and basically reverse the segment. So how can we do that? So basically, to handle that, what we could do is, hello, 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 hello. Reverse the segment. Okay. Okay. Let's actually repeat it. I think my voice lost for a bit, but now I think we are at good note. So now let's resume. Yeah. So what we were talking. So for any array that we have, to make it lexicographically maximum, we need the permutation or the array in descending order, right? Because we need the greatest element at the leftmost side, then the second greatest element. Basically we need the best possible element at each index, right? So the second observation we have to do is, basically we have to understand, like, how can we make this maximum, like how can we ensure that the array we have is the maximum. So the second observation is, it's just the thing that we have to start from left and then we go to the right, because to compare two arrays, right, to compare two arrays A and B, by definition, what we did here, where I explained the solution, we started from the leftmost side, and the index where both elements were different, we checked whose element was greater, whether either it was A's or either it was B's, and whosever element was greater basically was the lexicographically maximum or lexicographically greater element, greater array, right? So we have to understand that we are going from left to right, that we need the leftmost element to be maximum, right? We need the leftmost element to be the best possible element. We don't need to care for the rightmost one or the elements which are at right? At least when we have the chance to change it. Okay, so basically we have two observations here. The first is, the array, to make it lexicographically maximum, it should be the descending array. Got it? Because this ensures that we have the best possible choice at each step, as we are starting from left to right, which is the second observation, right? This also tells us that, like, if we start from here, let's say we basically make this transition, right? What the array would be? It would be 2 3 4 1, right? Is this the best possible array that we could do from here, right? But what if we change the first index? We basically took the entire array and we reversed it, right? Here, as we know that by rules to check lexicographically larger array, we check the index by index, and at whichever index the element does not match for both arrays, we check which array has the greater element, right? So this is our second observation, that we are going from left to right. So these are our two observations. Now let's check how are we going to reach to solution using these. Okay, great. So basically what here, like how we could get to solution, I got to the solution is Let's start from the left side. Let's actually put down the array 2 3 4 1 and check for each index, is this element the best possible element that it should be, right? Compare it with the lexicographically maximum array. The lexicographically maximum array would be 4 3 2 1, right? The thing here is this, the one more observation actually we can add it to the observation is that we can basically place any element once. What does that mean? Let's say we have array 3 1 2 4. Let's say we want to place here 2. What we could do is basically we start from this array, we take L equal to this index, here it is 2, and we move to the array that we want, to the number we want. We want 2 here, right? We wanted 2 here, so we wait till here, so R would be equal to 3, and then we reverse the array. So we got 3 2 1 4. We reverse the segment basically, and we got our desired array. So at one place, right, at any place we could change it to any element on the right side, right? Even on the left side we could do it, right? But right side makes more sense when we walk towards the solution, right? So we have to basically, this was our third observation, right? So what I did was I checked, like, what can I, is this index, we started from left and we check, is this best, is this best, right? If it was yes, we move forward, right? Otherwise we basically do the operation. Okay, great. The operation, the same operation that we did here, that we are going to place it with the best possible index, the best possible number it could have. So in this case of 3, what is the best possible number that this first index could have? It's the number 4, right? Yeah. So what we do is 2 3 4 1, we make an operation, same operation, we start from here, we reach till the point where 4 is, and we basically make the operation here. So what would this do? This would basically reverse the segment, and the number would be 4 3 2 1. And yeah, as we can do only one operation, this would be our final answer. Is this the greatest array? Yeah, this is. Coincidentally, that could be cases like after a point, like after some time, it would not be the best possible array, but we need the best possible array using one operation. So yeah, this is the best possible array using one operation. Got it? Let's also take we basically used all 3 observations. We started from left, we wanted the greatest possible number here, right? Because if we lose at this point, there's no point at winning at other point, right? So we choose the maximum possible number at the leftmost index at each point. Let's also understand from one more example, 4 3 1 and 2. Okay, we start from index 0. Is this best possible index? Yes. Okay, move forward. Is this the best possible number? Yes. Okay, move forward. Is this the best possible number? No. Why? Because we have 2, right? We are basically going to compare it for the, what is the best possible number at the index, right? We are basically going to compare it with this, the best possible array, descending array. So we are going to compare it with the number 2. Is this number 2 here? No. Okay, we are going to basically make a operation here, and after the operation it would be 4 3 2 1. Rest we don't need to care. After this operation we are done, and this is our final array. This is the maximum we could get, right? Because now the operations have exhausted, right? There's no point in making observations on the right side. Why? Because we need the maximum element here, right? If we lose here, the right wouldn't matter. That's what lexicographically has taught us, right? Hope you like the observations as well as the solution. Now also let's jump to the code and let's understand the code too. Okay, first we took the input and then the standard way. This is where we are checking if this is the best possible index or not. If this is the best possible index, what we need to do? We need to do nothing. We are just going to move forward. Otherwise, what we are going to do? We are going to place n minus I to the index. What this is basically, I'm marking on the L, right? How are we going to make the operation, right? We are going to make the operation. We have basically described that L is missing, right? And then what I do is in index I am going to basically in ST is our L here, right? The starting point, and the index is basically the number that we need. The number we need is 2. So I'm in index, I am storing 2. And then what I'm doing, I'm basically iterating the entire array, checking the position of 2. And then this index will turn to R, right? This give us ln R. And how we perform the solution, what we do, we basically keep on swapping the entire index. We got this is our L, this is our R. How are we going to basically reverse that segment? So what we do is we keep on swapping. Let's say we have A, B, C, D and E. How swapping works? Like how can we reverse using the swapping? So the concept here is, after reversing, the first element would be the last element. Similarly, the second element would be the second last element, right? So what we do is the first element we swap it with the last element, and the second element we swap it with the second last element, and we keep on going. So this is the code for it, right? After each we decrease our R, we increase our L. So the pointers, using 2 pointers, initially this is our starting point, this is our INDX or ending point, right? We swap them, this turns into the last element, this turns into the first element, right? And then we basically relocate the pointers. We basically increase the ST and decrease the INDX variable, the LNR here, and then we perform the operation on these two. So similarly we go forward, and whenever this L is basically equal to or greater than R, we stop, right? This is how we reverse the array. So yeah, here we basically reverse the array and then we are printing the final solution. Hope you got it. This was very beautiful problem itself. Reverse a permutation. Okay, great. Let's move to the problem C. Replace the sum. Okay. The problem C. Yeah. How are you going to solve it? Today KQ has an exam. Okay, there's this guy KQ. He has an exam at the Grail Academy. A strict teacher gave a task that KQ could not solve. He gave two arrays A and B of length n. KQ is allowed to perform the operations on the arrays. Okay, choose an index I and then replace AI with AI plus 1. Choose an index I and then replace AI with BI. And then, okay, great. Let's first understand this part. So there's this some guy. First, let's understand the problem statement. Okay, we have two arrays. This is a first point. We have two arrays A and B. Okay, and we have told that we can perform certain number of operations on the array. We have basically two types of operation, right? So again, operation forces, again we are to the point that we have operations. We have two types of operations. What are the types of operations? The first one is we can replace AI with AI plus 1. Okay, so basically let's say we have 2 comma 3 and we do the operation at this index, we can replace it 3 comma 3. So the next element basically is going to replace the first element. This is our operation. The second operation we can do is replace AI with BI. Okay, again replacement. Okay, so we can basically replace it, right? Let's say we have A equal to 2 comma 5 and B equal to 2 comma 1, and we applied operation on this index. So what would be the final A and B? A would be 2 comma 1 and B would be same, like 2 comma 1, the number it was before. Like if it was 3 comma 1, it would be 3 comma 1. Only this BI would replace 5 and it would result in 1A, right? So we have these two operations and we have two arrays. Okay, great. Now he has queries, Q queries. Okay, each query describe two numbers LNR. Again we are with LNR, and his task is to find the maximum value of the sum. Okay, great. And what's the maximum value of the sum is? What is the sum? It's AL plus 1, AL plus 2 dot 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 AR. So basically the entire subarray sum or the entire segment sum. If he can perform any number of operation on the element, since he is not skilled enough, he asks us for our help, not you. He asks us for the help. Okay, great. Many people were there with two questions, right? You can now see the solution for the third problem. So yeah, let's again check what we got. Now we have Q queries. This is our question. Ta-da. The Q queries, for each query we are given LNR and we have to find the sum of segment, right? So the segment would be like AL plus 1 dot 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 AR, right? We have to find the maximum sum of the segment, right? We cannot. Okay, this is we need to find. Got it. So we have two arrays, we can perform some operation. The one operation is that we basically replace the we can choose some index and then replace that index element with the next element which occurs in the index after it. And similarly we could basically also replace the current element of AI with BI. We have these two operations and we can perform any number of operations such that we get the maximum sum segment for each query, right? So this is the question. Hope you guys understood the question. So okay, let's also discuss the input and output. So the classic number of test cases, then we are given NNQ, then here is the entire array A and entire array B. So these are less than equal to 10 to the power 4, and then we are given LQ lines LNR, which are our queries. For each query we are given two integers LNR, and then we also given that the sum of values and the sum of values Q should not exceed 10 to the power 2 into 10 to the power 5. Okay, great constraints, and we are given 2 seconds and 255 megabytes. Okay, great. So how can we solve the problem, right? Let's actually see the observations, what we could get from the problem itself. So the first observation that occurred to me was that for any number, let's say we take this example, right? So here we had two arrays 3 to 1 and 1 to 3. In this question, the main game was to understand the operation. Like we could do any number of operations, right? Let's say we choose this. Let's say we have one operation where L equal to 1, R equal to 2. We need the maximum value of these two elements. How can we do it? Right? The one thing we know is that to replace this 2, right? Why? Because 3 is already the greatest number we could see. Right? Let's actually see like how are we going to approach the problem if we are solving it. So basically this 2, can we increase it by some number? Like we know that we have one operation that 1 could replace 2. Okay, great. Right? Let's say we had 5 here, 5 or 2. Can 5 replace 2? Yes, because we could basically replace 1 here and then we could replace 2. If 1 was greater, if 1 was 7, 8, 9, we would just replace this to it. We wouldn't replace 5 here. Right? So basically 2, any number this would be maximum of at any index I. This is our first observation. Would be maximum of ai plus 1 dot 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 towards the end. How? Okay, let me also read the comments and all. If you guys can't understand anything, if you guys have any doubt, you could just ping me out on the comments. I'm actively watching comments. Okay. Yeah. Let's resume. So basically this is our first observation, right? We could basically any number we have after it, we could basically replace it point by point and get it here. Right? So this is our first observation. We are just using our one of the operations we have, right? This is operation number 1, using operation number 1. Now here comes one more observation, right? Which is, let's say we have 3, 2, 1, 2 and 3. Okay, great. And we have, this is our array A, and now for array B we have 4, 2, 0. Okay, 0 couldn't be here, right? 1, 1, 5. One thing we have to notice that we can always replace this element by this, right? Let's say the sum we needed was L equal to 3 to R equal to 4. This segment, right? So we need the maximum element everywhere, right? Let's start with this too. How can we make this maximum? One observation is that from the first observation that we could basically replace 3 here, right? Yeah, that's perfectly fine. But are you like noticing it? It's like pretty obvious. But yeah, what we could do is basically we could first replace this 3 by 5. Right? After replacing it, that 5 that is here, we could replace this here. Got it? So this is our second observation. Right? So what does this tells? Let's take one more example actually. This is a very great observation actually. Yeah. Again we have A equal to, let's say 2, then we have 1, 1, 1, then we have 4, then we have 3, 3, 5. Now again, let's say this was our L, this is our segment. Okay, the L is equal to 1 and that's R is also equal to 1. How can we make sure that A1 is greatest? Right. Now we know that we can replace any element from first observation, any element which is on its right side, right, whose index is greater than it. So we could replace it by 1, but 1 is already smaller than it, right? So the observation, we also just noticed that we can also replace B first and then replace it. So basically we could replace 3 here and then we could place it here. Also one more thing is that we could also replace 5 here first. And that 5, again if it's on the right side of the element, we could basically replace it step by step and we could replace it here. right? We could keep replacing 5 by all the elements on its left side until a greater element is. In this case, there is no greater element. If this was 7, we would replace this by 5, we would replace this by 5, but we would not replace this by 5 because this is already greater. But that's also not a problem because we could replace this 7 here, right? This is actually greater number. So using this observation, we also came to a fact, right? So basically this index could be any of these indexes, any of these number, and also any of these number, right? So this is our second observation, which is AI could also be maximum of all numbers bi to dot 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 bn. Right, so these are two observations that we made. The first one was AI is equal to maximum of all the elements in its right, and AI is also maximum of all the elements in B starting from the ith index. Right, so these are two major observations that we are having. Right, using these two observations, what we get is for each AI, the maximum value of it would be maximum of AI plus 1 dot 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 and bi plus 1 . This is basically bi plus 1, the greater index, till bn. Similarly here till an. Right, so this is what we got. Right, so what the observation is, this is our third observation, right? Combining the first and second observation. Okay, let me also just fix my keyboard once. Okay, now moving on to the next part. So this was our third observation. Okay, great. So what we could do is, so what's the solution here and what's the final observation here is, let's say for each number 2 1 3 2 4 4 5 1, we could start from the last index, right? And we could take this, let's say we keep a number max, and for each number, for each AI, what we are doing is basically checking what could be the best value for this in the index in the array A. For an, the maximum value would be, it would be the maximum of an, which is the current value, and bn. Right, so the maximum value of an is here 2, and we place 2 here. Now as we reach an minus 1, we also store this 2 in our max, and max equal to 2. Now what, like using this definition, what would be the maximum value of an minus 1? It would be equal to max of an minus 1, the current value, an, and then bn minus 1, and then bn, right? But like, right, this is like the formula that we have. But as we know that an is equal to, we already are keeping this max variable, which already keeps track of the largest element we could get on the right side, right? This max is has already checked max of an and bn, so we have already checked an and bn. So instead of using these two, we could just basically check with max, right? Or the greatest, this max is what? This is the greatest element on the right side of the current element, right? If currently we are at ith position, this will tell us ai plus 1, right? Right. Like this is the very beautiful observation or very beautiful solution, like how we crafted the solution, right? So using it, we could just get the value of an minus 1. Then we could, using this, we could check it for an minus 2. What would be? It would be max of, again, an minus 2, which is the current value, bn minus 2, which is the, again, the current value of bn minus 1, and we can check it for max. What is the max? Either max or ai plus 1, or here I plus 1 is n minus 1, an minus 1, right? So what would this result in? What would this result in? This would give us an array A. This would give us a maximum value of array. This give us an array A with a maximum value of for each number. So these are all maximum numbers that we could get, right? And then what we would do is basically make a prefix array. Then the solution is very like easy. We could make a prefix array. What does prefix array does? It stores the sum up to this element, right? And for the for up to the index that we are. So this index, it will store the sum for this entire segment, a1 plus a2. How we do it? For we basically iterate from left to right, and we basically make sure that prefix sum for the current index I is equal to prefix sum for the last index, will tell us the sum for the number for the elements up to that index, so I minus 1 plus the current element we have, ai. But why are we calculating prefix sum? Let's actually move one step forward. Okay, we find the ai maximum. We needed all the elements to be maximum. Why? Because we need the maximum sum in each query. So what we did is we basically did all the operations what we could, and we got the maximum values for each element. Great. Now it tells us that we need to find the value, we need to find the maximum sum for each query, and each query we are given a segment. Can't we iterate the segment? No. Why? Because let's say we have n numbers, right? And each time we started from the first element, and for each operation L equal to 1 and R equal to n, right? And how many operations we have? We have n operations, right? The number of queries we have is at most n, right? The number of at most n is like I'm just assuming the n is equal to 2 into 10 raised to power 5, okay, or 2 into 10 raised to power 5. N is the constant we use to calculate omega. So iterating this array would result in n operation, and then we have n, so this would be n square. But the time limit is way less, right? N is 2 into 10 raised to power 5, and time limit is 2 seconds. So either way we won't be able to do the solution. So what we could do is we could solve it using prefix sums. How? To calculate any, let's say, what prefix sum does is, let's say we have an array 1, 2, 3, 4, right? This is an array A. The prefix sum would be 1, prefix sum of previous one plus this element 3, prefix sum of this previous one plus this element 6, and then 10. Let's say we need to find the subarray sum for this. How we could find it? We find the subarray sum for this entire prefix, and we, in this entire prefix, we reduce the subarray sum, the sum of this prefix, right? So this minus this remains this. This is what we needed, right? This is the logic for prefix array. For prefix, right? And how much time did it took to calculate the prefix sum? It took us O of 1, right? So it's pretty efficient. So if we did n times O of 1 query, this would be O of n, which is well suited for our current time case, current time complexities too. Got it. So this was the entire solution. So what we did, we first made each number maximum as it could, and then we make a prefix array, and then we basically perform all the operations just as I told you. Got it. So this was the entire solution. It was like, let's zoom it. This is how much we have typed, right? We started from here and then we typed and now we are here. Okay, let's also see its code. Up to F was actually pretty easy. Like after F, I think the problem started. Yeah, again here. Wait a second. Yeah, C question. We actually so yeah, here is our array that we have taken input. Here this is ai equal to max of this, and here's our max, the formula we created, ai bi and ai plus 1. This is our mx, or the greatest element we could have till ai plus 1. And then what we did was we calculated this and placed it here. So here we basically made sure that each element in ai is as great as it could be. After that, to calculate the prefix sum, we started from the first index to the last index, and we just calculated the prefix sum here. For each ln r, we calculated the prefix sum till r and then subtracted it from l minus 1, the prefix sum of l minus 1, to get our total answer, and then we just printed it. So this was the entire solution. Okay, great. Do anyone have any doubts? You can ping out in comments if you have doubt. Even after the live stream has ended, you can just ping me out in the comments or wherever you feel. It was great. Okay, let's move toward the fourth question. If we okay, yeah. So what does the fourth question tells us? It tells us that we have been gifted, you have been gifted, okay, I have been gifted, my honor, that gifted a new game called Editorial. I don't know how to pronounce it, but it doesn't matter. So in the game we are given n swords, okay, and then someone typed all fine, nice for C problem. Thank you. Yeah, that's off to you, man. Lead code 56. Okay, now okay, let's actually discuss the solve till C. Okay, yeah, you can basically now I'll explain the problem D. You can see how to solve it. If you solve till C, you could solve D too, believe me, it was not that hard. Okay, yeah. So yeah, we are given n swords, each with its own strength. Okay, in particularly the sword numbered I has strength ai. Great. And the game consists of n levels, each of which features a monster. Okay, so basically what this problem has given is that which problem it is problem number D, right? So let's first understand the problem statement. Yeah, we also got one more thank you. Great, man, thanks for the note. You can also like go for the problem D too. You solved two problems, right? You can understand this problem too. This one was also pretty good one, easy one. Like this was not hard one. The product queries was also like somewhat observation, but yeah, this one was actually good problem, the prisoner delivery one, comparing to it. And then G problem was actually a great one. So yeah, you can understand the E actually. Get hold of it. Yeah, now let's get back to the game. So yeah, so we are basically given a monster game. Okay, so we are given n swords, right? So this is our first point. We are given n swords, and we are the n swords are represented by an array A, where each element AI represents the strength of the sword. NGTH. Okay, got it. Now we have n levels too. Okay, you start at level 1 and progress further. To pass level I and move to I plus 1, you need to defeat the monster at level I. Okay, to defeat the monster at level I, you need to deal with BI sword strikes. Okay, the sword in the game are very fragile, so that they can only deal one strike before breaking. If you complete level N or run out of swords, you can finish the game and proceed to score calculation. Okay, great. So what does this tell us? That we are given N levels. Okay, great. And at each level, we are given this array B. Right. What this B tells us that for each level, let's say this was level 1. Right. This is array B. Right. It starts from B1 and we go to the Bn. And each element here represents that level. Right. So just like any other game, to go to the level I plus 1, we first have to complete I. Right. When we first complete I, we go to the level I plus 1. Similarly here, now here each level we have this BI. This tells us that how many strikes we have to make. How many strikes we have to make to basically clear this level. Okay, and we have given one more observation that after one strike, right? After one strike, the sword breaks. Okay, so what was the solution here? Like what the question says that we have n levels and each level we have a array B to represent each level, and each level tells us how many strikes we need to do to basically pass on the other level. And after one strike, the sword that we use to make the strike breaks. Okay, great. So in the game you are allowed to choose the difficulty level. Okay, if you choose the difficulty X, swords with strength less than X will not affect the monsters. Okay, the game score in this case is equal to X multiplied the number of levels you complete. Your task is to choose the game difficulty in such ways to maximum the game score. Okay, great. So what does this tells us? We have to calculate the maximum score. What we have to calculate? Score. Right? Why do we play games? To increase our score, to have the maximum score possible. Right? So what are the rules and regulations for the score? This is our third point for the problem statement. It's given that we can choose a difficulty. Let it be X. This is difficulty. Right? But difficulty. Got it? What will happen if we choose X as the difficulty? All swords, right? All AIs or this AI represent the strength of highest sword, which is less than X, are useless. It will not affect the monsters. But in turn, choosing this difficulty, our score here would be equal to X times X into or X times the number of monsters we defeat, the number of levels we complete. levels completed. Okay. Got it. So this is the entire question. We have first we have n swords, each has its strength AI, right? And we have n levels. To each level, the description is given as BI. Here BI tells us the number of strikes we have to make. And if after one strike the sword breaks, and the difficulty here, we can choose basically the difficulty of the game. The difficulty of the game, basically, if we choose X, all swords with strength less than equal to AI would be useless. We cannot use it anymore, right? And if the score, like in turn, using this, why would we increase difficulty, right? We should get something in turn, right? So in turn, what we get is the levels we completed, the score would be equal to X times the levels we completed. Got it. Okay, so we have to calculate the maximum score. Obviously it's a game, we need to calculate the maximum score. Now let's move and understand using some test case. Let's also understand the input and output constraint. The input is, I think, the standard t, number of test cases, n, a single integer which tells us the length of the length of array A and B, the number of swords, and the number of levels. And here is our entire array A and entire array B. And then we have to output the sum of n across all test cases wouldn't increase 2 raised 2 into 10 raised to power 5. Great. The classical we have to solve it in log n time complex, big O of n time complexity basically. And we have to output a single integer maximum game score. Great till here, right? So let's take this input 1 3 4 and 2 1 1. 1 3 4 2 1 1. This is our array A, this is our array B. Now we have to basically, to start the game, we have to start from first level, right? We never start from the third or second level, right? We always start from the first level. And for these are our swords that we have, right? Let's say we choose the difficulty equal to 1. If we choose the difficulty of the first sword, that means we would have 3 swords in total. If we choose this difficulty, how many swords we have? We have 3 swords. Why these swords matter? Because to win this level we would require 2 swords, right? Because if we have one sword, it would attack and this would basically break. Now we need one more sword. How many sword strikes we need? We need 2 strikes. So we would require 2 swords here, right? So after calculating difficulty, we need how many swords do we have? So for difficulty 1 we have 3 swords. So what we would do, we would basically attack from first sword, then attack from second sword, and this is basically cleared. Then we go here, we attack from our third sword, and this is also cleared. Now we don't have any swords. So what would be the score of it? The score of it would be number of levels we completed, 2 into the difficulty we choose, which is 1. So the score here, number of levels we calculated, 2 into difficulty we choose 1. The score here would be 2. Right? Okay. Let me also open the code here. Yeah. So what we have to understand from the problem is this that we are given some number of swords, and we are just let me actually fix my stream first and then I'll get back to you. open now. Let me also check into my phone. Yeah, great, I think. Yeah. So yeah, moving back to solution. So yeah, we here, let's actually place it here to 1, 3, 4. These are our swords, the strength of swords. And B, we are given, yeah, we are actually given a doubt. N equal to number of swords. They didn't mention. Yeah, they did, right? In the game, you are given N swords, right? So each with its own strength. In particular, the sword numbered I has strength AI, right? So yeah, we are given N swords, and the game consists of N levels. Hope that solved it out. So yeah, so what we have to basically we understood few, like the problem statement itself told us few of the things, right? That basically this is the more of a game of difficulty. We have to choose the perfect difficulty such that we are able to solve as many as problems as we can, and the multiplication of the number of levels we solved and the we got number of levels we solved and the difficulty would be the maximum, right? So let's understand it. Like what happens if we choose difficulty 2 here? Let's say what if x is equal to 2. See, we won't be able to use this sword, right? We would have only 2 swords now, right? So like if we had only 2 swords, let's say if B, the first one is 3, 2 and then 1. How are we going to defeat this 3? We can't, right? We only have 2 swords, and this, to complete this level, we require 3 strikes. Right, so the number of levels completed here would be 0, right? In the problem statement here, if you choose the difficulty x swords, the sword less than x, strictly less than x, will not affect the monsters. And the game score is equal to x multiplied the number of levels you complete. Got it? So first, this is our first level, this is our second level, and this is our third level. Actually, let me also plug in my laptop. I think my laptop has really low charging. Let me just get back in 1 minute. Yeah, I'm back with the charging. Let's actually continue the solution. So yeah, So what we did was basically, let's say we took x equal to 2. Now we have only 2 swords, and now we won't be able to even cross the first level. Okay, let's also see our first example that we had. So we had a equal to, this is our strength of swords, and this is our level, the number of strikes. Each element here tells us the number of strikes required to basically cross, basically to clear that level. Okay, great. So the first observation that we can do here is we have to basically smartly choose x here. Why? Because score would be x into number of levels. Number of levels we have completed. Right. Let me also see the comments. Yeah. Okay. Yeah. So continuing on to that, how could we basically solve the problem? Right. So the one, basically how would we solve it brute force? Let's actually start with brute force, and then we'll basically optimize it. To solve it brute force, what we could do is we could check for each x, for x equal to 1 to whatever the maximum constraint we have, right? 10 raised to power 9, right? The maximum value we have 1e9. 1e9 means it's 10 raised to power 9. And for each x, right, we could check how many levels, like how many swords we have. We could recalculate the number of swords. Number of swords. Right. Let this number of swords be s. From now on, we would be using s as the number of swords, as the replacement for number of swords. S is the variable x. And then we would iterate from the first, for the first level, and see are we able to clear it or not. I mean, we will keep on iterating, right? And if let's say we solved x levels, we completed x levels, our answer would be the maximum of previous answers, right, as well as the answer x into s, right, the score of current level, the score for current x, right? We could do it. What's the problem with it? The problem with it is there are a lot of x, right? There are 1e9x. We won't be able to even iterate this once, right? We cannot iterate till 1e9, right? We can max to max, we can iterate till 1e7 or something like that, right? So how are we going to solve it? So there are a few observations we can make. We don't need to iterate from 1 to 1e9. We just need to iterate. The first observation we have is we can just iterate the strengths. Why the strengths? Because let's say we have 1, 3 and 4. We can basically take x equal to 1, 2, 3 and 4 here. But this and this would result in same thing, right? What would x equal to 2 do? It would basically nullify all the swords which are less than 2. So all the swords which are less than 2 are this one single sword. So we would nullify it. Even x equal to 3 would do the same thing, right? Because there is no sword to nullify at x equal to 2. So there is no point at x equal to 2, right? We would always keep the maximum value. So this is our first observation, right? To basically take all the difficulty level equal to the strengths. First we will take the difficulty level equal to we will start from the minimum number, and we will keep on iterating to the as much as we can, and then calculate score. Okay, so great. but still there is problem, right? We have 1e5 numbers, we have 1e5 elements, right? This is equal to n, and then we have to basically calculate the number of swords, as well as we have to calculate this answer or the score, how many levels we matched, right? So how are we going to do it, right? It would basically again result in 1e5 into 1e5, again it would be n square solution, right? So how are we going to do it? Let's understand it step by step, right? The first step was to reduce it. Did we reduce it? Right, great. The second step is to calculate number of swords. How can we calculate the number of swords in less time complexity without using less, like what's the best and efficient way to calculate number of swords? How can we calculate number of swords? One like intuition we could use is, we know that we have to basically discard, right? Discard all swords, right? Such that their strength is less than x. So what we could do is first sort the array A, sort A, and then apply binary search here. Binary search. And how would binary search help in our solution? Let's say we have this 1, 3, 4 and x equal to 2. We could binary search and find the element which is just greater x, which is greater than this number 2, which is this. We got this index 2. So we got how many elements we are not using, right? So we could just do is n minus index we got 2 minus 1. This give us previous elements which are ai which are less than x, right? So this give us number of swords. And how much time will it take? It will take logarithmic time, log n, right? So it's pretty efficient for us, right? Yeah. Hope you got this all. Like, this is the second part, right? What we needed to do, we need to first calculate, we need to find for each strength. First we reduced it to 1e5, and then we have to what we did was this part, right? We reduced this part to 1e5. If we are able to reduce this part to some logarithmic time, we are able to solve the solution, right? This is the problem, right? The solution is this is the solution. For each strength we would basically calculate the number of swords we have, and then we are going to iterate from the first level, and then we are going to keep on iterating till we have some low swords left. But the problem with it is that it's taking too much time, right? We have to just optimize it. So yeah, we optimize this part. This number of swords part will take log n. Why log n? Because we are using binary search here to calculate how many swords we have. Got it. Now we have to find how many levels we could complete. Like, now we have to find x levels, right? How many levels we have completed, right? This part is still remaining. Okay, great. Let's actually see the third part, or the third optimization, levels completed. So the levels completed would be like, these are our levels. Let's assume this is our B. We need 2 swords attacks for first one, we need 1 for this one, and we need 3 for this one, right? What we could do is, one interesting observation is that what the number of levels we could complete is correlates to the prefix sum, right? Let's say we have a prefix sum B array. This tells us the prefix sum. So prefix sum array for this would be, we just used it in the previous question. It would be 2, this would be 2 plus 1, this would be 3, this would be 3 plus 3, 6. For those who don't know the prefix sum array tells us sum up till this index, the sum of all elements until this index. And to calculate this, what we do is we have this formula. Prefix array would be equal to, for ith prefix array, prefix for ith element is equal to its previous element plus current element. For this array it would be bi. Okay, this tells us the sum of all elements. So what we could do is, we got number of swords which is equal to s, right? This is number of swords, we got it. Now what we have to find is, what if we just binary searched it here? Let me repeat it. What if we just binary searched it here and find out how many levels we could complete? To complete till second level, we need 3 swords, right? Let's say we had s equal to 5. How many levels we could complete? We could basically binary search here and find the element which is strictly greater than it. So which is this element. And using this, using the same thing we used here, right? We could basically get how many levels we completed. The levels completed would be the index. The index here, it is 3 minus 1. Index minus 1. Got it? So like this was pretty much pro binary searched question, like each step. Got it? So similarly we use binary search here. Got it? So this segment that we needed, so the prefix sum b, basically the swords needed till that level. Yeah, right, exactly. The prefix b, this array, is the sword needed till this level. So the sword needed till second level is 3. We need 2 for this one and 1 for this one. And sword needed till third level is, basically we need 6. We need 3 for this one, this level, third level, 1 for this level, second level, and 2 for the first level. So using this, we created a prefix sum b array, and we used this. We basically place binary search here and found out how many levels could we complete. Got it? Got it. So yeah, again, applied binary search here. So this is actually plus, right? We are adding it. These two don't need to multiply. So we basically added log 2n here again. You guys are aware of binary search, right? Hope I don't need to repeat it, but yeah, those who are not aware of it, let's say we have numbers 1, 2, 3, 4, 5, and let's say we need to check the index of number which is greater than 3, right? So what binary search did is, it takes the starting index which is equal to 1 and ending index which is equal to 5, and it calculates midpoint. And if this midpoint is correct, is greater than equal to, in our case, right, we have to find greater than equal to 3. Then what it does is, it relocates the starting point as mid plus 1. And also we have this answer variable. This tells us that point 3 basically satisfies our solution. So let's say we did binary search here. What we would do is, basically we would discard this, we would mark this as our answer and we would discard this, right? We need number which are greater than equal to, or we would basically discard this part. In some cases it depends, right? Like if we need the greatest possible number, which is, in this case we need the number which is greater than equal to 3. So in this case what we would do is, we would discard this part. We would discard all the numbers which are greater than 3. We would discard this part. When put, instead of st, we would put en equal to mid minus 1. Got it? So this is how binary search works. If you guys don't know binary search, you can comment out to this video, and there might be in future videos about binary search. Okay, so yeah, so this is how we basically our 3-step plan that we used to basically solve the problem. What would be the final time complexity? Let this is n, so n into log n. Yeah, right. This would take 2 log n, but we don't consider the constants, so this would be n log n. Right, so the final time complexity would be n log n. So yeah, so this solution was basically the time complexity was solution. Like the solution was pretty obvious, but yeah. So yeah, here's our solution. Here we are taking input. Here we are basically calculating the prefix array for B, right? And here this is just a prefix array calculation, and then we sorted our array A, so we could basically do binary search here. For each, we started from 0 to n. Basically here we are iterating for each difficulty, and for I equal to 0 we iterated for difficulty 1. We just did it like it's the same thing, but yeah, I was little in hurry during the contest. I just wanted to type it fast, but yeah, this part is actually the main part. In this, int k tells us the number of swords that we have that are valid, right? This k, this is how we calculate it. Lower bound, are you aware of lower bound? Lower bound and upper bound functions in C++. Are you guys aware about it? So upper bound and lower bound, upper and lower bound, these are two functions in C++. Upper bound basically tells us, gives us the iterator, but you can always get the index for the element which is greater than, strictly greater than that some number, let's say y. And lower bound tells us, give us the iterator or the index for the number which is greater than or equal to y. This is the difference between upper bound and lower bound in C++. Okay, so basically this is just a easy way to do binary search, nothing else, nothing complicated, right? If you even like if you guys need, like if you are still not able to get it, grasp the upper bound and lower bound, you can basically, you can apply binary search yourself, right? The solution is straight. And you can also comment down like if you guys need some lectures regarding it. And then we have the upper bound function. What is this calculating? This is calculating how many levels it would be had. So this binary search for the number of swords we have, this binary search for number of levels we have, and then at max we are checking what's the max score we could have. So this was the entire solution for the question D. Hope you guys like the solution. Now we could move towards our question E. Yeah, so this was the entire solution. Let's actually see how long the solution was. Damn, it was pretty great one. But let's actually again move to the solution E. Got it. Question E. Now the solution. Solution is just a part. Today, Sabir Sen, I hope I'm pronunciating it wrong. So yeah, today this guy was called to the board with an array A of length n. Thanks dude, thanks LeadCode56. Was called on the board with an array of length n and was assigned an officer's task. I applied the same concept. Okay, great. Yeah, if you guys like have any other proof or any other way to solve the problem, you can actually ping it out in the comments. And also Mehin has also commented. Yeah, understood. Great dude, great. Yeah, now back to the problem. Product queries. Today we have this guy who was called at board with an array of length n and was assigned an officer's task to answer n questions. Got it? The ith question, it is required to determine the minimum number of elements from the array that needed to be selected from the board if it is allowed to use the same element multiple number of times so that the product is exactly equal to I. How to report that if it's impossible to achieve such a product? Note that at least one element must be selected. Okay, got it. So this is the question number E, right? Let's first understand the problem statement. Got it. So what's the problem statement? It gives us three things. First, it tells us that we have an array A of length n. That means we have this array. It consists of some integers. And then we have to answer n questions. What are these n questions? These n questions are basically we have to find for each number 1 2 3 3 3 4, each number 1 to n, we have to find if we could choose some elements from the array, right? Choose elements and their product is equal to I or not. This I is the ith question, right? This I is ith question. It could be from 1 to n. We have n questions 1 to n, and this I is ith question that we are having. Got it? So this is the entire question. So basically for each I, from 1 to n, we have to check are there some elements that we could choose, and we have to basically one more thing, we have to choose minimum number of elements, right? Here's this minimum number of elements. Okay, this is the entire question. Let's also see the, let's use some example here. Got it. Let's choose this. So we have 3 2 2 3, then 7 3 6 9, 7 3 6 7 or 9, 7, right? 7. Also, let's also see the constraints of the problem. So the constraints are the usual t number of test cases, n, which tells us the number of elements we have, and integers, and then the sum of n should not cross 3 into 10 raised to 5. Got it? Like the basic constraints, basic input taking. And then we have to find the minimum number of elements from the array required to obtain the product, or we have to print a -1 if it's impossible to achieve the product. Okay, great. So how many questions we have? Let's say we have one. For this we have 1 2 3 4 5 6 7 and 8 questions, right? 8 number of elements we had, so we have 8 questions. For question number 1, we have to find, can we choose some number of elements, some elements here, such that their product is equal to 1. Can we choose it here? No. So if we can't choose it, the answer would be -1, because here the minimum number, like the least number, is 2. We cannot choose any element here, right? And for 2, can we choose it here? Yeah, we can choose this element, and straightforward the answer would be 1. Okay. And for 3, yeah, is 3 present? Yeah. So we could just straightforward use it. The answer would be the minimum number of elements that we have to choose it, 1. For 4, we could choose this element twice, or one time this element, or one time this element. Anything works, right? It's mentioned that we could check one element any number of times. So anyways, using any permutation here, the answer would be 2, because we would basically require 2 elements in the subarray that we are choosing. Now for 5, we don't have any, we cannot take, 5 is a prime number, right? It does not have any divisibles. So we need 5 here, but do we have 5? No, so the answer would be -1. 6, yeah, we can, we have 1, we can take 1 2 and 1 3 here, and the answer would be 6. The number of elements used is 2. For 7, the number of elements choose would be 1, because that's present here. For 8, we can choose this element thrice, so the answer would be 3. Can we do it faster? No, because we have this. What if we had one 4 here? Now we can do it faster, right? Yes, we can do it using 2 3 times, but we have also have 4. We could use this once and this once, and we can also do it in 2 operations. So this is the questions basically, that for each question 1 to n we have to basically found, can we do, what is the minimum number of elements that we can take to basically find it. So for this problem specifically, let's also see the constraints again, that each ai is less than equal to n. Okay, great. So this each ai is less than equal to n. Why this matters a lot, why each ai is less than equal to n and greater, this matters a lot for the problem actually. This is our first observation. Our first observation is the input itself. Okay, how are we going to solve this? Right, this is some brute force approach. If you think, you could use some recursion or something like dynamic programming or something, right? So what I was thinking in the problem is, as we need to answer for each I 1 to n, what if if we think, right, there are plenty of things we know we have to answer for each 1 to n, we have to answer for each one, right? But let's say we have some number 3. Now we have to find out for entire array, how many elements should we take for the element 3, right? Instead of using this, what was my initial intuition was, the intuition I had for f was, for a prime number it must be present in the array. For the perfect square, its frequency in the array should be at least 2, or the number itself should be present. Okay, yeah, the prime number, the number should be present, yeah. For a perfect square, its frequency in the array should be at least 2. No. One more thing, dude. For 4 is a perfect square, right? But let's say we didn't had this here, and we also didn't had this here. Let's assume this is number 1. But we can choose a single element multiple number of times, right? This is mentioned in the question, that it is allowed to basically choose the same element multiple number of times. So even if we had 1 here, what we could do is we could use 2 multiple times. We could use 2 times, and this would result in, their product would result in 4. For a normal number, I started thinking about its factor and then got stuck. Yeah, even I started with the factors, right? When I was thinking, my first intuition was something doing with the factor. Either I would iterate from 1 to n, and for each number then I do some operation, right? These were my initial intuitions that I came up with. But there's actually a better way to think the problem. Whenever these type of problem occur, where we need to basically find for each 1 to n, right, what we could do basically is we could pre-calculate it, right? We could pre-calculate it. How are we going to basically pre-calculate it? Right, let's first sort all the numbers. What numbers do we have? We had 2 here, right? Let's use this example. What numbers we had? We had 2, 3, 6 and 7. Let's actually remove the duplicates. These are numbers we have, right? That means that, let's say we have this answer array. Here we are storing all the numbers. So answer 2 would be equal to 1. Right? Similarly, answer 3 would be equal to 1. Answer 6 would be equal to 1. And answer 7 would be equal to 1. Right? Whenever these type of problems occur, one thing you can notice, one basically observation that you can notice is, for numbers 1 to n, right? Whenever you need to find out the number of like permutations or something, uh, the important thing was like, what if I started from the last element, as we need the minimum number of elements, right? Because let's say we have like, what if, how many numbers can, what I thought was, using these numbers, can I calculate how many numbers can I basically make? How many numbers can I form using these numbers? Can I use that? That is what I thought. Like, how many numbers can I make? Numbers can I make? Can I make? Right. And while calculating these numbers, I'll also store the answer, this like how many number of elements I required. Number of elements required. Got it. So like a pretty how are we going to execute it from here? Okay, so what I thought was, everyone is aware of this theorem, right? Sieve of Eratosthenes. I'm probably going to write the wrong spelling, so I'm basically going to write it this way, right? What my observation was, this theorem is also used to basically mark down all the elements, right? So similarly, our objective is now to basically, how many numbers can I make using these elements, right? So using 2 3 7 9, 2 3 6 7, what I would do is I would start iterating from the last element 7, right? And I would mark 7 equal to 1, because this takes us one element, and I'll take a map or set here, right? It will store all the elements here, right? I put it inside the map, and what I would do, I will start iterating in the map, right? For each number, right? For each number, what I would do is I would multiply it by 7 and check if this multiplication results in number which is less than equal to n or not. If this results in s less than equal to n, I'll push this number, which is 7 into 7, into map again. In this way, what I'm doing in this way, I'm making sure that all numbers, like all numbers that I need, that I could form all the numbers. And using this, while I'm marking this in map, I'm also making sure the like how many operations required for this. I required 1 plus operations required for 7, right? So this was like the observation here. Like we could use the same thing that we use in Eratosthenes, right? Here. So like basically what I wanted was, I could start from last and I'll calculate how much elements that are required, how much elements are required for each number. So I'll first push this into the map, right? And check, push this into map and basically iterate entire map and see if multiplying any number, any key in the map, right, would result in number less than equal to n. If it's less than equal to n, that means that we are making it first time, right? And the number of operation required to go there would be 1 plus the number of operation required to make the current element, right? So this was the observation here. This was actually the master observation here. Got it? So similarly, as you know, 7 into 7 is 49 is greater than n, which is 8 here. We'll move to this, we'll move to 6. Again, we'll push 6 equal to 1 here. 7 equal to 1. Can we do 6? We'll again start iterating the array. We'll multiply 6 into 6, which is equal to 36. Again, greater than 8. So we'll break. Got it? We'll break here. will not iterate 7 more, because these elements will again be always be greater, right? Map, why map? Map or set? Why map? Because it sorts basis of the first, basis of the index or whatever, basis of the key, right? So that's why, that's like how we go here. Now from here, what's the next element? It's 3. So again we push 3 here, 6 and 7 remains intact. Now again I start from the first element, we iterate, we check if 3 into 3 is actually less than 8 or not. Yeah, it's again greater than 8. But what if it was less than, what if instead of 8 we had 10 here, we had n equal to 10, right? Then this would be less than equal to 10. So then we would push this 9 here and we'll make it 1 plus the number of operations needed to go to this number, which is mp3. mp is our map here, so we'll paste it here. So this, using this, will basically build the entire array, build the entire map. This will tell us how many elements are required to get how many elements are required to form this element, the key element, right? And if we are able to form this map successfully, we would just iterate from 1 to n and find its solution. Basically just output its solution using mp1 or mpi for each I, right? Any doubts thus far? Anyone? Anyways, basically this was the solution here. The solution was not to think upon using factors or using something else or like doing some operation. The solution here was how many numbers, like can we just building the numbers till n, right? And the time complexity satisfies same theorem that we are using sieve of Erasmus. What does sieve of Erasmus do? What it does is basically it tells us the number of prime numbers, right? Why? Because it keeps on calculating, multiplying. So the time complexity is n log n for it. Those who don't know can comment it. We could like have another video in this channel dedicated to it, right? Because it's a separate topic itself. Got it? So this is the solution for this question. So basically start from ending, start building the answer array or the map, right? First we'll push this and we'll check, this way we check how many elements can we create. Then also while creating we also check how many elements in the array are required to create this, and we could just pass it, and if it's not present in the map we would just print -1. So this is the solution for this problem. Let's also see the code. Pizza delivery. Oh no, this is actually E question, right? Product queries. Sorry. Yeah. So yeah, we sorted it. This is our map that we have. We are iterating into our map. This is how we are storing it. What I did was to store it. I also kept this answer vector just to keep it. We can keep this as single, but yeah, just for my convenience. And this answer, we check the current answer and the answer we are pushing, which one is the minimum we are pushing, so keeping that into the answer vector, and then again it dot first is less than equal to, and the same thing as I told, right? And if it's present then we are going to print it, otherwise we are going to print -1. So this is the entire solution. Hope you guys got it. Let's move towards the solution for F. So the problem F, let's first read it, understand the question, and then we'll move. Yeah. Courier YI was on the title Best Pizza Delivery Person, GR. The manager does not like him, so he gave him very difficult task. The manager provided him with n coordinates xi yi, where he needed to deliver the pizza. He will deliver the pizza in the following way. GR is prepared at the point, pizza is prepared at the point AX, AY, and YF starts the delivery at this point. Okay, to deliver the pizza, he can move from the point XY to 3 points, X plus 1, Y, X, Y plus 1, either we could go X, Y minus 1. Okay, after he has delivered all the pizzas, he returns home to the point BX, BY. Okay, each point takes him exactly 1 second. Handing over the pizza takes 0 seconds. The manager wants to deliver as fast as possible. You need to find the minimum delivery time for all GR pizza. It is guaranteed that the delivery is always possible. Okay, great. First, let's understand the problem statement. So the first thing we are told is, basically we need to deliver some pizzas, right? So initially we are at point AX, PX, AX, AY. These are our initial point, right? And then we need to deliver pizzas, and then we need to reach to point BX, BY. This is the flow, right? You need to basically wander around we visit some coordinates and then we move. And we are given a move. The move we are given is, if we are at X, Y, right? Either we could go X, Y plus 1, either we could go X plus 1, Y, either we could go X, Y minus 1. Got it? And we need to find the minimum time. Right. So again, this is our operation. Again, operation forces. And then we are given this. So this is our entire question. Whatever you're seeing in the screen, this comprises of entire question. Now, how are we going to solve this? First, also read the input. Actually, the constraints are very beautiful here. So we are given the general constraint, number of time cases, AX, BY, BY, BX. We are also given that all numbers are 1:9, and then we are given coordinates for all the points that we need to deliver the pizza. And also just notice this thing, our initial point, the X coordinate of our initial point and X coordinate of final point, all the points between it will lie between it. Okay, got it. And then we need to find the minimum time to deliver the pizza. Okay, great. So what are observations here? The first observation is X always increases, right? We cannot reduce X. So if this is our basically timeline, we could go here, we could go up, we could go down. These are the three. Why this graph in geometry problems, imagining or using this graph or like sketching it really helps. This is like a tip, right? So this is how I thought. First, X is always increasing. Okay, great. So what I need to do, all the points that are we going. Let's say initially we are at point 1, 1. Then we are at point, these are the points we are given. We are given 3, 2, and we are given 2, 4, and we are given the final point, this B point, this is A point. This is the A point, right? The P point is, let's say, 5, 5. One thing you need to notice is that we need to visit in increasing terms of X. Why? Because we cannot go backwards. This is our second observation, right? That we need to visit in terms of this increasing order of X. Visit increasing order of X. Why it doesn't matter, right? We could go up and down, so it wouldn't matter like why we are choosing, right? So now third thing that we have. Now third thing is basically like, how are we going to solve the problem, right? So first sort them on basis of their X, right? Let's say in this problem we had 1, 1, we had 3, 2, and we had 2, 4, and at finally we have 5, 5. Let's plot this into a graph. Let's say this is our graph. Initially we are at this point, right? So we are at x equal to 1, right? Now we also have x equal to 2 here. Let this x equal to 2 and let this be x equal to 3 and let this be x equal to 5. Right. Now what we have to know is, if we start from here, we can only go rightwards, right? At x equal to 2, let's say we have one more point, 2 comma 1 or 2 comma 0 actually. So we have this point here, we are at initially at here, and we have 2 comma 4 around this point here, right? And we have to basically we can go right side, and then we could, now here comes our fourth observation. This third observation is basically plotting it makes it much easier. And the fourth observation we are going to have is basically, now when we go here, when we reach point here, we can either go backwards then go to the top, towards the top, as we need to cover all the points. There might be one more point here, 2 comma 3, but it doesn't matter, only the topmost and the lowermost point matters. Why? Because we need to cover all the points, right? So if we go down here, so we go first the downmost element and then we go topmost, and then we are residing here. Similarly, we could go up and then we could return back to the lowermost element, right? And then let's say here we have 2 points here. Let's say we have 4 points here again, right? So either any case, either we would be in this element, either we would be here. Now there might be one more like question. This is the second. We would be either would be on the extremes, right? Either extreme top or extreme bottom. Right. Now one question you might have, which would be, let's say we have these points. Can't we have this as our last element? Right. The question is fine, but let's think. Can we have it? Let's say we are at here. We go here. Now we have to go all the way up, and we have to go all the way down. Now this is the drill, right? We have to cover all the elements. We go up, we come back, and then we go all the way down. Now to go back here, we have to travel all the way down, right? So this doesn't make sense, right? That this is the ending point. So we make sure that either the topmost element or either the lowermost element is the ending elements, right? And what we do is we also calculate the time for reaching the topmost element, the time for reaching the downmost element here. And when we move towards the next one, for this point, what we do is we check how much time it would require to reach from the topmost element and how much time it would require for reach to the bottommost element. And the minimum of those two would be the time required to reach here, right? In the same way, like we go using this method, again we calculate the minimum time to reach here and here, and similarly keep going, we find the minimum time to reach the last element. Got it? So this was the solution here. The solution was that only extremes matter, and then we calculate the time to reach this element, and then we calculate the time to reach this element. And for the next, again extremes matter, so we calculate for this element how much time it would require for both points to reach here, and how much time it require for the lowermost point to reach here, right? Even though it was like the sixth question, like comparatively this was the only solution here, right? Because like we could just iterate and keep this, and so basically a dynamic programming solution, right? So keeping the states, but you don't even require dynamic programming. You could just, like, I used variables to store states, the previous state, only previous state matter, right? So this was the entire solution for it. Let's actually see my implementation. It would actually clear more. It would, yeah, here what we did, this is our two vectors we posted, right? So these are how I am creating levels. This I said na, we need basically x, we need to differentiate points on basis of x, and then we need to find the extremes. So this is how I'm storing it. I'm storing it in the map, right? So this creates a distinction for us, right? And then we are sorting it so we could know the extremes, right? So this is again, this is our up is our topmost element. Current initially it would be b is the element I have taken the input here, and uptime is the time to reach the upmost element in the line. Got it? On in the x-axis, on the y-axis basically, right? Similarly, the dwn is the downmost element, and downtime is the time required to reach the downmost element. And I'm just updating it again and again. So again I updated this for each let's say x, for each line we are iterating for this line, and this line. So for each line we calculate the lowermost element. This f is the first or the downmost element, L is the largest element, and then we calculate it. Nu upt is the new uptime, the new time for the upmost element. It would be the minimum time to travel from. This travel function basically tells us the time taken to travel from one point to another. How this is calculated, I'll tell. And but this also tells, this time function tells us go from starting point to ending point while making sure that we go to the midpoint too. Why we need to go to the midpoint? Because we need to cover all the points, right? So if we are basically, let's say our previous level had 2 points, but this time we have 3 points. To calculate time from here, I have to calculate first I need to reach down and cover all the elements way back and then get to up, right? Similarly for this, first I need to reach down and then calculate all the elements and then reach up. This is what it's calculating. The new downtime is calculated here, and then we basically update the topmost element and lowermost element, as well as the uptime and downtime for both the points coordinates. And then x, as we know that we have only one operation, so I check the final element minus the initial element where the x was. We cannot reduce it, we can only add it. So this way I added, and then we print the answer. Right, here's our function total. So first we need to reach the point mid, right? So first we did mid. This is what we calculated the absolute difference for mid to the current point, and then we calculate from mid what would be the absolute distance to go to the last point. So in this way the entire solution was implemented. So yeah, hope you like the solution. Now we'll move towards the last solution, which is the question G. Okay. Paths in a tree. So this is an interactive problem. In this interactive problem, you are given acyclic connected and directed graph consists n vertices. We define a path between V and U as sequence of distinct vertices P1, P2, P3, Pk, such that P1 is equal to V and Pk is equal to U. For all I, there exists edge between Pi and Pi plus 1. Let's understand this problem. This problem was little hard to understand for many people. Let's understand and break down to it. So the problem statement tells us that we are given first we are given acyclic connected undirected graph. Now any graph which is acyclic and connected and it does not have any self loops and other things, it's a tree. So we are given a tree with n vertices. Got it? And we have to calculate, we define, this is the definition of path. What is path here? Let's say we are given 1, 2, 3, 4 and 5. This is a path. Why? Because when we extract it, we have 1, 2, 3, and each of those adjacent elements have an edge in common. Got it? So this is the simplest path. All the numbers are distinct, right? So we don't repeat them. So this is the path we get, right? Now we are given two hidden vertices x and y, and they may coincide. That means that they might be same, and you have to basically follow queries. What queries? Choose two vertices a and b. The jury will we have to make queries. Basically, jury will respond 1 if the part between x and y and the part between a and b shares one common vertex, otherwise it will respond 0. Okay, and we can make at max n divided by 2 plus 1 queries. Okay, and we have to basically then follow the standard interaction principles for the interactive problems. Okay, so the input we are given test cases, then we are given n the number of vertices in graph, and then we are given the description of graph using n-1 edges or the tree here. And then what we could do to basically ask the question, we have to basically use the question mark a and b, and basically to print the answer we could take an exclamatory mark and the vertex what we think. We just have to find the one vertex. So what the question is we are given a tree, and then we can make some queries. For each query we can give two numbers. We can make query using question mark a and b, and this we are one more thing, there are two vertices x and y which are hidden, and in each query what it would make a simple path from a to b, and it will make a simple path from x to y. If any vertex intersect or is common in both paths, it will print 1, right? If not, it will print 0. So this way we could make some queries to the graph, right? So this tree or the graph, same thing that we have n vertices, we have description of the tree, and then we are given queries to find out. But we can only make queries which are n divided by 2 plus 1. We have these many queries to make. Got it. So what does this query mean? Like, let's actually understand it. Let's say we have graph. Got it. Let's say the x was equal to 1 and y was equal to 2. If we make a query as a equal to 5 and b equal to 3, this means that this path, right? In this path it will check with the initial x and y path, which is this path, and we'll see are any elements common. Yeah, this 2 is common, so this is going to print out 1. And what we need to find out is any number that exists in the path, right? This is what we need to find out. Any number, it could be 1, it could be 2. We need to find out in n divided by 2 plus 1 queries, basically. So how are we going to solve this? Right? So again we need to make some observations. So yeah, let's do it. What observations can we have here? Okay, so first come first, I think the first observation that we have to find out is we basically in one more thing, like there could be only one element here, right? So to find out any basically what we could do is, let's say for this path, for any path. Let's say again we have this tree 4, this is 5 and this is 6. Got it. You chose this part 1 2 3 6 and it gave as 1, right? It gave as 1, right? So what we could do here, let's say we chose this part 1 to 6 and we were lucky in the first try we got 1 as an answer. Now how can we find the answer? Like how can we find like what would the path would be? So there's this thing. We would basically, what we could do is we could use binary search again binary search forces. How we could use binary search? We could basically, let's fix this, right? Fix this left side and we could check. Let's take a path from 1 to 3 and if this results in 0, that means that this vertex was basically responsible to give 1, right? Because this entirely gave 1. If this didn't, this means that this vertex lies into the simple path. Let me also elaborate it one more example. 1 2 3 6. Let's say this entirely gave 0 1 and then you check this also gave 1, this you check, this also gave 1, but you check with yourself, you gave 0, and as this was the largest, like smallest element which gave 1, so this is the answer. So that means that this lies into a path between x and y. So this is the entire question, right? This is like the first observation we could have, right? So the first observation state that if we could just found any path with 1, like any path that produces 1, then we can find using binary search the solution, right? So this is the first point, right? So now what we need to do, we need to basically how much this operation would take. This operation would take log 2n, right? So this is actually fine. Like okay, got this is like first observation we made. Like if we got the path and it resulted in 1, that means that some vertex is basically intersecting with the x to y path, right? So we could use binary search to get the answer. Okay, great. This was like the first observation. Now coming on to the second observation. The second observation was finding paths. Finding paths was the second observation, right? So how are you going to find paths? Let's discuss it, but first let's understand this more deeply. This was actually the single most important solution, the single most important thing that we needed. Also let me show you my code here with well commented code for the same thing, like how it went, right? So first, like this observation you got it, this is just an implementation, like how are we going to finding paths, right? There are plenty of things that we could do. Let's say we have this tree. One thing that we could do is basically for each we could make some pairs, right? For each leaf we could pair it with the last leaf, right? We could do a DFS call here and store all the leaves in a vector, and then in DFS call the leftmost leaf would be stored first. It would be like 7 8 and 6, and we could make pairs of this 7 and 6. If any pair, if any simple path resulted in 1, we would basically extract the path right? And after extracting the part, we would use binary search to find the answer, right? So this is, but we need to make something sure, right? What we need to make sure in finding paths, cover entire tree, right? Like in this case itself, in this case we made a path to this, so this entire was covered. Let's say we have 8, so 8 made the graph with itself, right? This also resulted in 0, this also resulted in 0, right? We used 2 operations, but we left this one, right? What if, yeah, let's assume this was the R culprit, this was actually the path, this was X and this is actually Y2. These like both could be the same, right? The simple path exists of single vertex, which is this itself, right? How are we going to calculate this path? This path was actually remaining, right? This path left, right? To calculate these path, what we could do is using either LC or something, we could basically calculate all the paths that we have covered, right? These all the nodes we have covered, this is also we have covered. So what left? 4 was left, right? So the remaining nodes we have, we could cover it in one go, right? Use this to basically implement it again. There are like lot of things that you could do. You could do a simple BFS query to store distance from the root node, and basically the smallest distance, the node with the smallest distance to largest one. The smallest distance to largest one, you could make a simple path here. This will basically cover all the paths, and if this results in 1, that means that we could basically apply, extract the path and get the answer using binary search. So the flow of code was something like this, right? Make pairs or explore all path, explore entire tree. This was a first step. Got it? If any path gives 1, right, that means that some intersection was there. Give 1, what you do is extract the path, use binary search to implement it, right? So if any path, one of the path will actually be intersecting, right? Because we are covering the entire tree. For any path, cover entire tree. Right. So this was the entire solution. Explore entire tree, or make entire tree, or make entire this. This was the entire solution that we have. Right. Let's also see how did we implement it here. So yeah. First, we have like 2 functions here. We have this answer function just to print the answer. These are like helper functions, right? Because this is an interactive problem. Whenever you have interactive problem, you have to basically flush. You don't like for interactive problems. What are interactive problems? Interactive problems are when you are also asking the jury, right, for some problems. Like in this case, we are asking if like this was the format that we are using, and we are asking if A and B does the simple path in A and B, and does the simple path in X and Y have some intersection or not, right? These are called interactive problems. And after asking, or let's say outputting, what you need to do is you have to flush all the outputs using cout.flush. Got it? So this is what like interactive problems are. Nothing great. So yeah, you had query, you had answer. Got it. So this helper function is to get the path, right? Whenever, let's say, any simple path results in 0, I said we need to extract the path, right? So this helper function is used to extract the path, the get path function. After that, we are using binary search on the path to find the intersection vertex. Again, the solve path. How are you going to solve the entire path, right? So we are using binary search here. And then again, DFS2. Oh, we have a question. I am in second year, but I understand the problem G was not able to solve till I was not able to solve till E, but to understand the problem F and G. Okay, great dude. If you are in second year, if you are able to solve till problem, like if you are able to understand it, it's really great. You are doing really great. And yeah, these problems, like, don't get disheartened. Like, next time you might solve it even, right? Try, like, after the contest you might try to upsolve it, right? That's great, dude. Just, go with the flow. Doesn't matter. Try now. You can now try the solution. Okay, you can now, like, try after reading. Okay, this was the entire for this G problem. You have to just this one was actually the solution. This was like the entire key idea for the problem, right? The rest was just implementation, like how are you going to implement it, right? Again, you are going to make a DFS call for the solve path. Again, you are going to make a helper function for, like, to get the path, and then you're going to again implement it binary search, right? These are topics, like, if I keep on going on, it will take entire net, and I would just be explaining binary search and then all. Yeah. So yeah, again, the algorithm, we need some algorithm to make pairs. Either you could use this algorithm that I told. This also works. Yeah. Basically pairing it, and then for the rest of elements you go for the first, the smaller, the distance, whose distance is the smallest to largest, and you make this as a path. This will always make a path, right? And then you may go forward and forward, like in this case, right? In this case, this element was not even considered, right? So you form for the rest of the elements, you make them make a simple path of that itself, and then again you apply the binary search to get the answer. So again, yeah, there are, like, couple of things that we could do. There's, like, again the same thing again and again. So yeah, we make pairs, we then solve, and then we move forward. This is actually not my solution, this is solution I found online. Yeah, it's pretty much some LLM, because how to detect LLMs, this catch, no human is going to try and catch. But yeah, this solution I found very easy to, like, understand and formulate. So I basically am showing this one. But yeah, this is probably some LLM. This is like, nobody writes code like this if C in equal to T. I hope everyone got the solution that they were looking for. If you guys have any other approach for the problem, or if you think, like, for any of the problems you could have done it better, or you want to like discuss it with with us, or whatever, you can just ping it out in the comments. You can ping it out in the comments. And if you think, like, there were some topics, like in this contest, right, we were using binary search a lot, right? We use a lot of binary search today, right? And, like, yeah, almost in all problems use binary search, right? So yeah, it was a great topic. Like, if you need detailed videos for binary search, you can ping it out. If you think, like, my solution was not that good for any of the problem, you can ping me out that right? So we could discuss regarding it, right? You can post it in the comments if you think you have better solution for any of the problems, if either it's A, B, C, D, E, N, E, F, or G. And also ping out like what was your favorite problem, like what you did or solved, what you loved solving, right? So the observation on the final comments on the problem set would be A, B, C, and D. I would guess like till F it was pretty easy this time. G was like a little bit observation and implementation too. And yeah, so yeah, that's all from me. So yeah, binary search. It was very heavily binary search implemented problem. So this was the final solution. We can actually discuss more on this implementation part actually. Let's discuss more on it. Yeah, we use DFS here. Binary search plus DFS. There's also one observation here, like in this tree, the thing that I was saying was in this tree, like these trees, many of these trees exist where we were actually leaving nodes. This was actually also a star observation, apart from the binary search plus getting a simple path observation. Yeah, this was actually I was missing. I was just thinking like, am I missing something in the solution? Yeah, just note down like, yeah, this is also a very good observation that we were missing some, right? And then we just have to make it an extract and then basically do binary search on it. Okay, hope that helps. Let's actually end this. Hope you guys love the solution. If you feel free to reach out if you think you have better, free to comment, you have better approaches, or if you want to discuss some variations of the approach, or even if you want to like discuss something else, or you want to share your solution or your approach, and you think if that's more efficient and more beginner friendly or more good rather than mine, it's like it has very good chances, right? So yeah, there are like dozens and dozen ways to approach a simple problem, right? So yeah, that's all from me, signing off.